Okay, so LeetCode problem number 1, where we are getting a bunch of numbers. There might be duplicates there, and then we have to find two of them. We can't use the same one twice to add up to the target sum. So, a good example of this, 3 to 4, and we have to add up to 6. Because we can't use this 3 twice. We have to take the 2 and the 4. And we guarantee there's only one solution. So use an anonymous function, a lambda, and we're taking a left argument, which is the target. We denote that with alpha, and we take a right argument, which are the available numbers, and we denote that with omega because those are the left and right most characters of the Greek alphabet. And in two ways I'll show how to do this. Both of them are using an O(n) squared solution. And then we can also show a solution that has smaller complexity than that. So let's start off by making all the different sums. And we do that with the outer product. So we write that with dot and then a plus. And then we need the numbers from the right on both sides. We take all the combinations of the numbers on the right with all the combinations of the numbers on the right. But we don't need to repeat ourselves like this. There is a kind of combinator, a higher order function, which takes this function and uses this argument on both sides. And that's this confused phase, commute, it's called. So this gives the same thing. And then we can compare with the left argument. And that's all great. So here we can see that we have 2 plus 4 and 4 plus 2, but also 3 plus 3. And that's the one we need to avoid. So for that, we're going to make another outer product. This time, we're going to find out how many numbers do we have. And then we're going to generate the indices for that. And now we make an outer comparison. And this will give us the diagonals. But we're only really interested in the upper diagonal, upper right side. So we can, instead of doing an equality table, we can do a less than table. So this gives us the upper right triangular matrix without the diagonal. And we can use this as a mask together with this mask, which indicates that we have achieved the right sum. So if we put these next to each other, then we can see how these correspond, and then using this mask to indicate with an and, we only get this single one. That's the one we're after. So we put an and in between them, and that's the coordinate that we want. Now we can use the where function that tells us all the coordinates that have a 1 in them. And this says 2, 3. The example given shows 1, 2, but that's because APL by default uses 1-based indexing. We can change that index origin to 0, and then we try again, and now we have this. Also, we have a box here. That's because it really wants to have multiple elements available. So if we don't mask out here, we get all the different places that are 1. And so in order to only get 1, then we take the first element from that, and there we have a solution. Another way that we could do this would be to generate all the indices where we have the correct sum, and then remove all the indices from the diagonal. So how can we remove the indices from the diagonal? We could remove the ones where the two elements are the same, but it's easier just to generate the indices of the diagonal. So if we take if we take this here, which then generated the indices of the array. So let's put them next to each other. And then we can double them up. So we can do a 2 reshape on each of these. Those are all the positions that are invalid, and then we can just stick a set difference without in between them, and that gives us all the different solutions that are valid. We only have to return one. It doesn't matter which one, so we just take the first one, and that's a different solution. Okay, finally, it's a little bit more complicated. We can take the prefixes of the right argument, and we do that by using a running concatenation reduction. So this is a concatenation, and a forward slash would be a reduction. Backward slash is the running, just like a running sum instead of a sum. That gives us the prefixes because we're concatenating, well, the first element, and then the first and second element, and then first, second, third element. And now we can take these prefixes as the last element is the active one, so to say, and we need to sum it up with all the elements that precede it. This ensures that we never get any element added to itself. So we can introduce another little function inside and apply it to each one. And here we want to take the last element dropped from the argument, and then we want to take the last element, which we can do that as we can either say -1 take instead of drop, or we could do a right side reduction. So we take the right of all the elements, rightmost of all the elements, and then if we add those up to with each other, then we get the different possibilities here. We could also write this a little bit more elegantly if we make this a dyadic fork, it's called, a 2-argument fork. So if you take a -1 here on the left, then we can say we want -1 take, which would be the last element, and -1 drop, which is all the leading elements, and then we can just add them to each other right here. Okay? And now all we need to do is to find out where are the left argument equal to these. And here we really need to find the coordinate of this 1. And it's the easiest way to do it is again to do an ON squared solution, but this time we're only using bits, so it's not so bad. So if we mix this means that we're taking this list of lists and we're combining them into rows of a matrix, and then padding with zeros. Then we get this matrix, and then we can go and say where do we have a 1, and that's the same thing as before. And this time we get it in reverse order, but again, that doesn't matter. And we could also go in and say these are our lists of the ones that have a 1, and then we can say where, so this is an OR reduction on each one of the lists, and that gives us the third one, so this is the second coordinate, and then in that third one we can ask what are the true coordinates in each one, and that gives us this one here, and the other one's empty. Only one of them will be true because we know there's only one solution. So this means we can combine this coordinate with the coordinate of this one. So we can go back to this one. So that gives us the 2, and this one gave us the 1. We just need to flatten it a bit. So this is in list. This flattens it. So this gives us the 1, and then we can combine that with the 2 that we got from here. And this gives us a solution which is a lesser complexity than ON squared.